Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
As a professor of network, so Mark's going to tell us a little bit about XORP. Well, I'll just let him.
Thank you. So good morning. I'm going to spend some time this morning talking about XORP, which is extensible IP router software stack that we've been working on for the past, I guess, about 5 years now. This is going to be the research spin on this rather than the marketing spin. I hope that's the right one for this audience. If you want the marketing talk, I can do that one, but it's probably much less interesting. So basically, I'm going to start off by trying to explain a little bit about why we bothered to do this in the first place, and then go through some technical detail about how we actually tried to design router software to be extensible, why that matters, and sort of design decisions that that's entailed, which make life harder for us, but I think in the long run are going to be really valuable. Where we came into this was somewhere back in 98, 99. A load of us network researchers were bemoaning the fact that it was increasingly hard to do network research, and the research that was happening was getting increasingly divorced from reality. If you went along to Nanog, you hear one complete story. You go along to SIGCOM, you hear a different story, and they just were not intersecting at all. And this is a bit of a problem. There's really seemed like they were getting a particularly big gap in the area that involved the core of the network, especially routing and that sort of stuff. And if you look back through sort of the 80s and so forth, pretty much all of the important internet protocols came out of universities or the research labs. And what happened was basically people built stuff. They tried it out. Some of them worked, some of them didn't. The ones that survived ended up getting standardized. That's not really the way things happen anymore. If you look at sort of this gap between what's happening in research and what's happening commercially, there's a bunch of different reasons for this. The principal one is really that the internet became commercial, and so the stability of the network became really important, and experimentation became more and more hard to actually do in a real network. If you look at the likes of Cisco and so forth, the major infrastructure vendors, they're not really motivated to support experimentation. They don't need to, but also it's not where their money comes from. Their money comes from the ISPs. If you look at what happened in the research labs throughout the world, as this problem started to evolve, we started to move towards doing a lot more work in simulation. There's probably a few people doing congestion control research, for example, that haven't done a lot of work in simulation, and also in routing and so forth. And the network simulations got quite good. But the problem is that simulation really isn't a substitute for experimentation. There's a lot of questions you'd like to ask that you can't answer unless you've actually got either real-world traffic or real-world routing information, that sort of stuff. And if you look at what happens in an awful lot of universities, PhD students basically give up. They implement their stuff in NS. NS has 1 million parameters. I don't know if you've played with NS, but it's like how you set these parameters is, to a large extent, guesswork, because there's not enough information about how the real networks function to be able to set the parameters correctly. It's not that the students are stupid. It's that there isn't enough information to go on. And so the end result is that the research that gets published may or may not bear any relation to reality. So the key here is we really would like to be able to run experiments in real networks. But, of course, we've got this problem with not being able to do that for a whole bunch of different reasons. Now, if you look at where the state of the art is with network research and actually trying things out, for the end systems, this isn't really such a big deal. The open APIs that you have on all operating systems basically let you do protocol research that uses those APIs. So things like SIP, which I was fairly heavily involved with, RTP and so forth. That sort of network research is very easy to do. There's no real problem with that kind of stuff. Even the stuff that involves kernel changes, things like TCP SAC or the IGMPv3 work, you've got open source operating systems that let you experiment with that. There's also quite a good history of experimentation on the transport protocols and so forth out of the commercial labs, including here, of course. But the real question here is, what about the protocols that affect the routers? And if you look back to where we started in this whole process, there were really two options you had. The first option was you went to Cisco and you persuaded them to implement your protocol. They now shipped an experimental iOS core. you persuade the ISP to actually try that out and convince them that their routers are not going to crash and they're not going to lose lots of money, and you do your experiment. Your other option was basically to implement the routing part in one of the available open source routing stacks, MRTD, GateD, Quagga, so forth. Implement the forwarding part in your favorite operating system or in some of these extensible forwarding paths. Now persuade the network operator to put your PC in place of their Cisco and run your experiment. So how likely are either of these to actually happen? Well, about that likely. So we're faced with this problem. It's really, really hard to actually manage to do this kind of experimentation that we want to be able to do. We want to be able to play with routing protocols. We want to be able to play with doing interesting things in the forwarding path and so forth, and see how they respond to real traffic. So if you look at the possible ways you could solve these problems, the first way basically would be if the router vendors opened up their development APIs, and that would then let third parties actually develop for the existing backbone routers. Unfortunately, this isn't really in the vendor's interest. Certainly the big players, it's not in their interest, and the small players don't really matter as far as having any impact. The other option is basically to try and get an extensible router software stack actually out there and deployed. And so this basically would mean you'd have to design a software stack that was extensible. You'd have to design it so it's robust enough for real-world use, not just use in universities and research labs and so forth. And once it gets to this degree of robustness, then you persuade some adventurous network operators to actually deploy this stuff. And over time, it gets more and more robust as people use it initially and probably in research labs, but more and more into production use towards the edge. And so the goal here is that in the long run, you've got a platform that's actually out there in the real world, designed for extensibility from the outset. Sure.
And why didn't Quagga satisfy that first part?
So Quagga is, well, firstly, it was really not going properly at the time when we started. But the second reason why it doesn't really satisfy that is it was never designed for extensibility. The one thing that Quagga does, which is fairly good for extensibility, is it's a multi-process architecture. So you can put new routing protocols in there. But if you look at all the internal communication that's happening and configuration stuff, it was not really designed with this in mind. So as I go through my talk, I'll show you a whole bunch of advantages we made, which are very different from what they did, which we think really will help as we go forward. G2?
There's two different things going on here, right? There is one where the routing platform is stable, and the second is that the routing protocol is stable.
Yes.
The ISP could be very happy with some platform X, and they would yet be very wary of deploying a new routing protocol because it will still wreak havoc.
That's right, and that requires appropriate isolation boundaries internally and things like that, so that when something goes wrong, you limit the amount of damage it can cause. You can never limit the amount of damage to zero, but you can significantly reduce it. Certainly, if you're trying to do experiments with something like iOS, where everything is in one memory space, basically anything goes wrong and everything dies. We can do a lot better than that. We probably can't get totally to the point where there's no risk with doing an experiment, but we can reduce that risk.
Current solution to here with your solution to 2 spikes back, and it's not obvious what the difference is.
The key really is that you design this stuff to be extensible in the first place, but then
You can make that argument for some of the different things you're having to do with MRTD, gatekeeping, and so on, but that comes down to what's the
yeah, I guess this comes down to how effectively our solutions actually solve these problems. And hopefully I'm going to convince you that they solve the problems reasonably well, but I have to get through the talk to convince you of that.
By reasonably well, we mean significantly better than the other.
Significantly better than the alternatives.
That's about solution one. Who you tried working on Cisco?
We've done a lot of work with Cisco, but Cisco have immense internal problems on structuring of their software anyway. A better vendor to talk to would be Juniper rather than Cisco, because they actually have an architecture which internally has appropriate isolation boundaries and so forth. And originally when we talked to them, they thought that they might be able to go that path, but it seems that again, it's not really in their interests. They've succeeded fairly well in managing to carve up the core router market into a duopoly. And so long as it is a duopoly, then they don't have a particular interest in shaking that up and opening up the platform to third-party software vendors and things like that. But it could happen. I mean, one of the options is that we're sufficiently successful that we persuade them to do it. And then it doesn't necessarily matter whether our software runs or not, because they've already solved the problem. Although the big problem, of course, is that this doesn't really let the basic core router functionality get changed. It may let you experiment with routing protocols, but not necessarily with the forwarding path, for example. That would certainly be very nice if they did. I don't think it gets us all the way to where we would like to be, but it's a lot better than where we're at the moment. So going back to this issue of how hard it is to actually change the core of the network, from ISP's point of view, stability really matters, and they can't afford these can't afford problems. They basically are not going to run anything experimental on their production routers if there's a high risk of it actually affecting their existing traffic. So you really need to have appropriate isolation boundaries if you're ever going to get to that particular position. Of course, early on, I think there's very little chance of us actually getting any of this stuff into the core of the network, but that's not necessarily such a big deal because all of the interesting evolution at the moment seems to be happening at the edges of the core rather than right in the middle. Observation here is actually building routing protocols is really hard, and it's actually much harder than I thought it was 5 years ago. You read these specs and they don't seem all that complicated, but actually when you come to really build this stuff, it is not at all easy. If you look at the sort of history of people trying to deploy routing software, the reason why Cisco and Juniper do so well is because nobody else actually does very well. Their software gains a reputation of being trusted over a long period of time, and we basically need to get to a similar sort of situation with that. But the big vendors don't really have a lot to gain from innovation here. Because the ISPs can't afford to run experimental code, the vendors don't actually want to bother putting the effort into doing experimentation and so forth. The normal way this would change in just about any other part of the product space would be through startups. And that can't happen here. And the reason it can't happen here is because this is a closed software market. If you buy your hardware from Cisco, you have to run Cisco's software on there and all their routing protocols and their management stuff and everything else. Similarly for Juniper and so forth. So the end result here is that there's a lot of important problems that are cropping up over the last 5 to 10 years, which are really remaining unaddressed. I mean, there are really serious issues with BGP, for example, that it would be good to actually get addressed. And it's just not happening because there's no real incentive for the people who can make a difference to actually make any change. So our hypothesis here, and we'll see whether we can convince you of this by the end, is that if you design for software for extensibility in the first place, that we can help solve this problem. Again, it's not necessarily a complete solution, but it takes us in the right direction. So this hopefully would allow experimental deployment of new routing protocols. Obviously, it's places where the stability matters a little bit less first, and as they start to gain a reputation for stability, then creeping out further through the network. There's also a hope here that we might be able to enable a market for router applications, which is something that doesn't exist at the moment, but it would be very interesting if you could actually do that. If you look at what's available, really, there are extensible forwarding paths that exist. Intel and a bunch of others put a lot of work into network processors. There's FPGA-based forwarding paths. There's a bunch of software stuff, Click from MIT, Scout, and so forth. But really very little work on trying to design extensible control planes has happened. The actual demands of router software make this actually pretty hard. Obviously, the stability requirement we talked about. Routers are really doing a very large-scale distributed computation, and anything that involves distributed computation is hard. So trying to design stuff that is going to be stable and extensible at the same time doesn't exactly make your life easier. If you look at the way routing protocols are written, the specs and everything else, they're written with an assumption of a very tight coupling of functionality. This probably comes, if more than anything else, from sort of the legacy of implementing it in a tightly coupled way in iOS, which is where an awful lot of these things that we have to deal with now came from originally. And the protocols themselves were never designed to be extensible, so trying to actually design software that's extensible for things that weren't designed to be extensible in the first place is interesting in its own right.
Do you have any tangible ways to measure extensibility?
This is really hard. Towards the end, when I'll show you some slides on evaluating this, I'm not going to show you any slides on how to evaluate whether we've been successful in extensibility, because there is no really good sort of quantitative metric for that. The best we can really do is anecdotal evidence that basically shows that when people have tried to do things with software that were not what we expected, that they've generally found it very easy. They've either been able to slip them straight in without any changes to the rest of the code, or that it has required some changes, but the changes have been very minimal and easy to do. And that seems to be the best we can do. If you know of any other ways of evaluating extensibility, then please let us know, because we'd like to know. But we don't know of any. So anyway, this basically brings us down to the 4 challenges we're really trying to solve with this. We're trying to basically build software stack that has sufficient functionality to actually be deployed in the real world. Design it to be extensible from the outset, and one of the key things here is to try and decouple the extensibility to avoid this massive feature interaction problem that you get into whenever you deal with extensibility. So extensions have to be able to coexist pretty gracefully. Performance has to be good enough. It's not the primary criteria for control plane software. Initially, we're not really dealing with core routers, but just the edge routing problem is hard enough, and even edge routers often have to deal with full BGP feeds of 160,000 routes and things like that. So big routing table size matters. Increasingly, low latency of routing really matters. It didn't used to, but as voice over IP and things like that start to be a large amount of the traffic, then it matters that if anything changes, that you reconverge very fast. And then, of course, it's got to be robust. And that basically comes from having a lot of good test suites and so forth, but it also comes from deploying it in the real world and finding out all the really strange things people do with routers that you never would possibly expect. An aside here, in the past, a lot of the routing protocol implementations were scanner-based. And so basically what happens then is that periodically a scanner runs over the routing table and accumulates changes and then notifies neighbors and changes the forwarding table and so forth. This is easy to implement. It doesn't take much CPU utilization and so forth, but it has pretty poor route convergence properties. This didn't used to matter, but the market is really changing. People really want things to be able to converge very fast when things change. So these days, basically the whole trend is towards event-driven router implementations. Actually, not that many of the implementations out there are event-driven, but they're increasingly going that way. So basically, when something happens, as far as possible, you process that event through to completion immediately. This means you really need to be explicitly tracking the dependencies between the different pieces of functionality. So this, again, is something that's harder to implement, and it's especially harder to implement in an extensible manner. So this is just something to bear in mind, that we're trying to design things which are event-driven from the outset.
But then one of the advantages of having a scanner-based solution is that if there's a sudden surge in the number of updates, that's not going to impact your performance.
Yeah, there's inevitably this trade-off. Actually, even the scanner can get itself into trouble when a lot of things change. But I think the balance in terms of control plane, if you look at the way sort of CPUs evolve and the amount of CPU power you have processing control stuff, the same thing doesn't apply for the forwarding plane, where bandwidth has been growing faster than Moore's law. But in the control plane, the routing tables are growing fairly fast, but they're not growing anywhere near as fast as CPU cycles that are available to throw at the problem. So I think the balance of power has changed here, that in the control plane, where basically we can do stuff that is more expensive than we used to be able to do. And so, whereas before you really got concerned that you would overload the router control plane because when a large number of things happen, you won't be able to cope with it. These days, I think that the balance between trying to make sure things converge fast and trying to make sure you don't overload your CPU comes down on the side of being event-driven. Now, that means you're going to have to be fairly smart about how you cope with overload. And I won't claim that we're as smart as we need to be to cope with that. It's something that we are aware of there being some issues when we actually have some proposed solutions to how to deal with that. Mostly that comes down to scheduling. You've got to have a pretty good internal design of how you schedule stuff in a router. But that's getting sort of ahead of myself here. OK, so this is what I've come to talk about, XORP, which is our extensible open router platform. This was, we implement basically all the main core unicast and multicast routing protocols. It's a multi-process architecture. Everything is event-driven as far as it is feasible. It's a BSD-style license, so you can take the code and do whatever you want with it. At the moment, it's about 560,000 lines of C++. About a fifth of that actually is machine-generated code from various stub stuff, so it's 400 and something thousand lines of stuff that we've actually written. Probably about another 40,000 to go in there with some other things that have not yet been committed to the main archive. So this is the sort of stuff I'm going to talk about today. The main contributions here are the stage design of how we've built our routing protocols. I'm going to talk about our inter-process communication mechanism and how that being scriptable is really a very nice feature for us. I'm going to talk about how you actually build an extensible management framework for a router, how dynamically extensible command line interface and the management software. And I'm going to talk about our policy framework as well. So we think that this is basically the first router software stack that's really been designed from the outset, thinking about extensibility as being a high priority and also being event-driven. You can get the stuff from there if you wish. So this gives you kind of a roadmap to the different pieces of XORP. There's nothing desperately surprising about this particular map. Over here we have the different routing protocols for unicast routing and for multicast routing, PIM sparse mode, IGMP, and so forth. They contribute routes into the RIB, the routing information base, which then arbitrates when you get a route that's available through more than one protocol and things like that. That passes the routes down to a process we call forwarding engine abstraction. Each of these boxes on here, by the way, is a process. The purpose of this is really to give us an isolation layer so we can separate our functionality from the platform we're actually implementing it on. And this turned out to be really, really useful when we suddenly got the bright idea of implementing this on Windows. The management plane up here involves a router manager for starting and stopping processes and configuring things, a command line interface, SNMP, and then things for doing our inter-process communication here. So this is basically the roadmap of the different pieces of the software. It's a multi-process architecture so that when something goes wrong in one particular protocol, there's a limited amount of damage it can do to anything else. And then the inter-process communication mechanism between these processes is one that we ended up devising ourselves, which was not something we set out to do in the first place, but we ended up there anyway. And I'll talk about that a little bit later as well.
So here you show what you did the unicast one, so about 1.5 multicast records. I assume that the multicast routing one is all similarly extensible.
Yeah.
Who does the arbitration for the multicast?
The answer is at the moment, none, because there is not a specific requirement for it. In other words, it's pretty much never the case that you have a router that actually deploys more than one multicast routing protocol. Now, what we would have probably done if we actually were implementing more than one is to basically do the similar thing for the RIB for multicast. But it's very unclear to us at this stage exactly what the requirements of such a box are. Yeah, the issue, though, is it's really unclear how you should actually arbitrate between different multicast routes. There is no, not at this point in time anyway, a consensus as to exactly how to do that. I know there's an RFC that you wrote, which says some of this stuff, but as far as I'm aware, nobody actually deploys it that way. So the answer is it's up in the air, and it didn't seem to be any point in actually writing that piece without actually having that part of the story. Now, should that requirement come up, it's very easy to simply redirect that arrow to point to the multicast RIB where we actually accumulate routes. At the moment, we haven't done it simply because there isn't a requirement to do it. So yes, it's the architecture would permit it. It would require that we actually decided what such a RIB should do. And I don't think that's a terribly hard thing to do.
Here's another question. You talked about robustness and getting confidence to do this. So what is your testing methodology for all this stuff? When you do the functionality, how do you get that confidence that you're
So what we have is a large number of component tests which get run for each of the different things we build. Whenever we build something, you build the component test for it. Whenever we find a bug, the first thing we do, we try to stick to this. We don't always succeed, but we try, is to actually write the component test that identifies the bug, then fix the bug. And so we've gained a very large number of these component tests for testing out the individual components. So that basically prevents accidental regressions and things like that, which is pretty important when you've got a large code base. The next thing we do is then we have a bunch of test suites which tend to test the whole protocols. And this is all script-driven, and the fact that our inter-process communication mechanism is scriptable, which I'll get onto in a little while, really helps us because we can write, we have a large number of Python and Bash scripts, which basically then can drive the inputs to all of these protocols and test them all through a whole bunch of different hypothetical scenarios without having to have a real network there. So one of the things that the FEA does, this is, again, a little bit of an aside, but anyway, in a normal implementation of a routing protocol, OSPF would talk to the network, BGP would talk to the network, RIP would talk to the network, and so forth. We haven't done that. These routing protocols, instead of talking to the network directly, relay their communication through the FEA. They send an enterprise call to say, send me this packet out of that way. This means that the protocols themselves are very isolated from the platform they're running on, so it makes it very easy for us to port things to different platforms. But perhaps more important than that, it means that we can exercise the routing protocols themselves in isolation. We can fire these IPC calls at them from scripts to drive the inputs and test that the outputs do what we would hope. And that really is a very nice, flexible way that we can actually do testing. So we can then do a lot of automated testing. If you check out XORP and build it and type gmake check in the top-level directory, it'll go through and run hundreds of tests on the different protocols, exercising the protocol's inputs and seeing what pops out to the other side and so forth. And we have a tinderbox which runs every, whatever it is, 6 hours or something, on about 8 different platforms now, that goes through and exercises all of those different scripts and checks that on all these different platforms, all these tests actually pass. And anytime we discover something strange going on, we then go and add more tests to this. So this whole test suite is growing as we go on, as we find strange things that people do with protocols that we never expected. Does that answer your question? Okay. So I'm just on the introduction of my talk still. So what I'm going to talk through today is, first of all, I'm going to talk through a bit about the routing protocol design, how we actually break these up in such a way that you can extend them later. Then I'm going to talk a bit about the management framework and how we actually design an extensible management framework, given that we don't really know what people are going to try and plug into it in the future. The third thing I'm going to talk about is the policy framework and how to actually build a policy routing framework when you don't really know what people are going to try and apply policy to in the future. And lastly, I'm going to give just a few performance results, which were from the paper we had in NSDI recently, just so that you can get an idea for how well things work. So the first question I want to discuss with you today is the question of routing process design. And basically, this is how do you actually go about implementing a routing protocol in such a way that it can be extended in the future? And that's not normally been done. People, when they implement a routing protocol, basically try to implement exactly what the spec says. And they don't really think about the fact that these things actually evolve. But also what we want to do is to encourage that evolution. So this matters more, what we're trying to do, than even in the commercial implementations. If you look at a conventional router, in this case I've sort of simplified it down to, this router is running BGP, which is the bluish color here, and RIP, which is the greenish color here. But normally most routers are running more than this. Essentially, what happens in most routers is you have incoming routes come in from neighboring routers, and you end up with a state machine for handling the communication with your routers. And they contribute routes into a big pool of routes. And then the decision process for RIP basically looks at RIP routes and then decides which ones win and passes them on to the neighbors and also passes them down to reporting. BGP does a similar thing, except for it not only needs to know about BGP routes, but it also needs to know about the IGP information to be able to make its decision. So it needs information from both pieces of this to be able to decide what to tell its neighbors. And then out of this, the best routes end up getting passed on to the forwarding engine. So you look at this and you go, well, how do you design that in an extensible manner? Because there's really this sort of big accumulation here where you've got all the data in one place. So this is a pretty tightly coupled architecture. And that performs well, but it's really hard to change unless you understand exactly how everything interacts with everything else. And this is kind of the key lesson for extensibility. If somebody's going to change something and they have to understand everything else first, they're never going to be able to extend it in a safe manner. You need to isolate the amount of stuff somebody has to know to be able to make a change down to the minimum pieces of relevant information. So what we needed was an architecture that was going to allow us to do future extension and minimize this information somebody needed to know. And we ended up choosing a Dataflow architecture here. Now this, of course, given that Eddie Kohler was at ICSI at the time, this came out of the fact that Eddie had used the Dataflow architecture for the click forwarding path stuff. In his case, it was routes, it was packets that were going through the Dataflow architecture. In our case, it's essentially routing information that's going through. So basically, what our routing processes, these routing tables, like I showed on the previous slide, are actually now composed of these sort of dynamic small processes through which routes flow. And the interface to each of these stages is common, so that you don't actually need to understand very much other than where you need to plumb in something in and what things are going to go backwards and forwards. So I'll discuss this with the example of BGP, although it also applies to other things we've done. In BGP, what we have basically is information coming in from the peers. So you need stuff to handle the state machine and so forth, dealing with each peer. Then you have incoming filters where you actually want to modify routes or drop them if they don't pass whatever your routing policy is. So you end up with a bunch of filter banks here. The routes come into a decision process where also information from the RIB comes in about the IGP distance and things like that. Decide which are the best routes and then fan those out again to the peers and also back down to the RIB to be used for forwarding. So that's a very simple sort of breakdown of how BGP might be split into a Dataflow architecture, where stuff is basically coming in, flowing through these stages and through. So the key thing about this diagram is that each of the arrows on here is a point for extensibility. Wherever you want to actually put something in here is a point where you might be able to plumb in new functionality to extend what's going on. Now, if all of those arrows were different, then you'd have to understand an awful lot to be able to do it. But in practice, they're not. So what I'm going to do is to zoom in on one of these arrows and basically show you what's going on there. So here's an arrow. The key here is what exactly does the interface look like? So essentially what you have is messages which flow down the pipeline. And it's very simple. You get messages that say add route and delete route. And so anybody who's going to plumb anything into this pipeline, all they really say is, well, OK, I need to implement add route and delete route and pass the things on down the pipeline as appropriate. Now, the other question is, where are routes stored? If you store them after all the changes have happened to them, then it becomes actually pretty hard to figure out how extensions fit in. Because one of the things you want to do with real routers, as opposed to a bunch of the PC implementations, is to reconfigure them on the fly, which means what the stages are doing in the pipeline changes, depending on how the configuration of the router changes. So what we ended up doing was to actually not store the routes post-modification, but to store them right back at the beginning. And we store in each of the incoming peers a tree of routes. And those are unmodified. You store them on the router before you've actually applied any filters to change them or things like that. Now, what this means is that if any of the downstream modules get changed, you then just have to push the routes again to apply those changes, especially if you want to reconfigure filters on a router, which is a pretty common thing you need to be able to do on production routers. So those routes can be pushed down. And this basically means that when you want to do a decision as to whether this route wins and so forth, you need to be able to send a request back up to another peer and say, do you have a copy of this route, to find out which one wins. So you end up with this lookup route message, which flows back upstream and the reverse of the add route messages. So going back to this diagram now, this lets us put new functionality trees. These add route messages flow down, lookup route messages come back up. And you can put new functionality in any of these individual stages if you want to change how the router actually functions. But if you look at this diagram, there's one thing on this diagram which is complicated, and that's this decision process. It's taking information in from the RIB. It's taking information from each of these peers. And the problem with this is it turns out that this stuff is asynchronous. Each of these are just a flow, but this actually needs to sometimes look up information in the RIB. It needs to send stuff out. Also, it turns out that one of the big problems with an architecture like BGP is that the rate at which you can send stuff to your peers varies depending on network congestion, how fast they are, and so forth. So you end up having to queue stuff, and if you queue stuff multiple times for each peer, then things get pretty hairy pretty fast. So the point at which you need to queue stuff turns out to be back here. Otherwise, you run out of memory very fast if you have a large number of peers. So we end up decomposing a decision again. So now the decision process is very simple. Stuff comes in, it sends the relevant lookups, figures out whether it wins or not, and then sends messages downstream. And then there's another set of stages go in here to do looking up of the BGP next hop information. So a route will come down here, and it will get to here, and it will say, do I know about that next hop? And if it does, it will pass it through, and stuff. If it doesn't, then it gets paused here temporarily while we do a lookup. So this now doesn't have to do anything asynchronous. It's now much, much simpler. And we also put a queue in here, which is how we deal with the fact that, stuff can come in faster than it can go out, and we have to be able to deal with that and not blow large amounts of memory on queuing stuff individually for each of the peers. So it turns out there are more stages than this in our real implementation, but this gives you a good idea of how we've actually gone about designing stuff for extensibility. Now, when we were doing this, we had sort of missed something when we first thought about this problem way back about 5 years ago. And so I've just shown you the first half of that diagram. The problem now is, what happens when this peering goes down? Because the network failed, or the neighboring router failed, or whatever, something went wrong. This guy can have an awful lot of routes stored there. If it's a BGP feed at the moment, it would have 160,000 routes or something stored there. So the first problem is that you can't actually delete 150,000 routes instantaneously. And we're trying to be event-driven here. So there are some events you just can't actually process through to completion. The second problem is that the peering may come up while we're still deleting those routes. And it may go back down, it may come back up, it may go back down. And you can see how this can get really complicated really fast if you have to deal with all of that sort of thing. So I was bemoaning how we were going to do this, and then Otto came up with a really nice suggestion, which what we do is we take that entire routing table, we take it out of the peer in, and add a new routing stage there. Pop that routing table back into that. This is now ready to handle anything else that happens. This has the original route tree of the routes we'd learned there, and this can now go off and do what it wants in the background, deleting things as appropriate, as fast as it sensibly can, given the CPU resources we have available. But it's not actually having to deal with trying to do this stuff all in one go, because we're now able to just go off and handle new things. And so the peering is now ready for routes to come back up. This ability to do these dynamic stages is just a really nice, flexible thing in this architecture. It lets you handle all sorts of things that you wouldn't easily be able to handle in a very simple manner. We use a similar way when when a new peering comes back up. We stick in the stages, so that stage is responsible for telling that neighbor all about all the new routes. And once all the existing routes, rather. And once the neighbor now is updated with all of the state, then that stage can go away again. So I just showed you that in the case of BGP. In the case of our RIB, we use a very similar stage design. We actually do sort of pairwise merging of things here, which actually provides even more different places you can actually put extensible functionality in. With BGP, you can't do that kind of pairwise merging of routes because, well, BGP is sufficiently broken. But you really need to know all the possible alternatives to make a decision, because I won't go into why BGP is broken. It is. And then what this lets us do is to have other routing protocols register interest in routes that match certain criteria. And so we can add these different dynamic stages into the RIB so that we can inform the other routing protocols about subsets of the routes, things that match different criteria here. I can talk about exactly how we do that later on if you want, but I was not going to go and do that today. Okay, so that's basically this as a staged architecture for trying to implement routing protocols, which we believe actually gives us a lot of flexibility in terms of how to implement things. Moving on, the next thing we want is to be able to design an extensible management framework for our routers. And if you look at how real routers are used, you basically want to have a single configuration file for a router. It has to be able to configure all the functionality, BGP, RIP, new experimental routing protocol, forwarding, all that sort of stuff from one configuration file. Because that's just the way operators interact with routers. They deal with the router as a whole. although as software developers, we have to deal with the router as a series of components. So what this means is we can't have separate command line interfaces for those components. We can't have separate configuration files for them and so forth. We have to basically deal with this stuff as one. But we have to do that even though we don't know what people are going to come up with in the future. What we really like is to be able to drop in new routing protocols in the future from new vendors, experiments, whatever. And we want to be able to drop those in without having to change any of the core code in XORP. They just want to be able to run. Our command line interface is now aware of their existence and can do all of that sort of thing. So to explain how we do that, first of all, I have to explain a little bit about our inter-process communication mechanism. As I say, we didn't really intend when we started out on XORP to write our own IPC mechanism. We ended up kind of getting forced that way through a whole different a bunch of different requirements we had on the problem. But what we have is what we call XRLs, XORP resource locators. And these look very much like URLs for the web. And for those of you who remember the web in 1992, 1993, the great thing about the web back then was actually it unified things like Gopher and Archie and all of those sort of things into one framework. And what we were trying to do in XORP was to be able to integrate all sorts of other pieces of code we manage with whatever protocol it was you'd use to actually configure that. So this is one of the reasons why we ended up going for things which have similar properties to URLs, the fact that they can actually address different transport protocols, different ways of configuring things. In the end, it turned out that actually the thing that really mattered was that these are ASCII, or at least they have a canonical ASCII representation, and that's been the most useful thing about them. So anyway, we end up with things like this, which basically, that's a sort of the canonical ASCII representation of an XRL. The way these are implemented internally most of the time is actually in a faster binary form, but there is this version works. So basically, there's a part of this which basically says what the transport is. Finder basically says we don't know what the transport is yet. It needs to be actually resolved. Then that can be implemented over TCP, UDP. You can implement an XRL protocol family to send signals to processes, that sort of thing. There's a module. Who am I actually trying to communicate with? Whoops. Love that feature of PowerPoint. There's an interface name, which is a specific interface that a module might support. Some modules, some interfaces might be supported by multiple modules. Some modules might support multiple interfaces, and so forth. Then, obviously, the bit that starts to really matter, the method we're trying to call. In this case, we're trying to set the autonomous system number on BGP, and then any appropriate parameters, a type parameter list for the type of thing. So that then gets fired off by the process trying to make the call, and the XORP finder basically says, well, okay, how do I resolve that into a particular transport protocol with the appropriate parameters? So in this case, it's got resolved into something that's transported over TCP with the relevant port name and an IP address. This also means, of course, that it can actually work over the network. Our internal communication can work over the network, so we can build distributed routers if you wish. And anything else that it might do in terms of munging the method name and so forth. Do we support V6 addresses in there? I don't even know whether we do or not at the moment.
Not yet.
Could ask about over there who implemented most of this. I don't think we do at the moment. Yeah. It's basically the same as happens with URLs, and they have the same problem. There's a syntax for those two. It's only syntax. The syntax can be revised. So the original strong motivation for trying to do this was that we wanted to be able to support extensibility by dealing with non-native communication mechanisms with things. So examples here might be sending signals to processors or using SNMP, and you can then integrate something that needs to be configured through SNMP through exactly the same inter-process communication framework. And the XRL library would then hide that, how that communication was actually happening from processors, so you wouldn't have to care about that. It's actually turned out that the biggest advantage of this has been the fact that they have an ASCII canonical representation, which was a surprise to us. It wasn't what we expected. But what this means is that we can build these test harnesses by basically being able to call these XRLs from scripts. there's a little piece of C++ code called call XRL, which takes one of these on the command line. And you can basically script this stuff to do all that kind of testing. The other thing that it enabled us to do was to design our router manager process in such a way that it can just take a configuration template file for each of the processes on the system and learn how to actually control it. So what this does is when you introduce a new routing protocol into XORP, you put a binary, obviously, to run, but you also put one of these template files which simply says, these are the things that can be configured on this process, and these are the XRLs you can actually use to configure them. So this is a very, very small snippet out of a XORP configuration file. And this is sort of a very similar syntax to what Juniper use on their routers. It's just the usual sort of hierarchy of things you would actually configure. But then for this OSPF instance, you then end up with a configuration template file, which basically says, well, these are the things you can configure under the protocol's OSPF part of the configuration. You can configure an OSPF area. There's going to have to be a variable stuck in here, but it has that type. And then for each area, you have a bunch of interfaces where there's going to be an interface name, which has type text, and so forth. And then on each of the interfaces, you can specify the hello interval, which is obviously it's an integer. But then for each of these different things you want to configure, then you can say, OK, the way you configure that is basically to use an XRL, and you fire off this XRL, and you embed the relevant variable names from this stuff into this XRL to do the configuration. And these ASCII template files are very easy to write. But it means that we don't have to, the router manager itself has to know nothing at all about anything it's going to control. All it has to do is know which directory to go to load all the different template files in, and suddenly it knows everything it needs to know about how to configure one of these new protocols that's on the system, which is really very sweet. That will allow, hopefully in the future, people to write third-party routing protocols to run on a router. You ship somebody the executables for the routing protocol. You ship somebody the ASCII template file. You put it in the relevant directory, and suddenly you've extended the configuration interface of the whole system. So that's a whirlwind tour of the management and how we tried to make the management part of the system extensible. The next question was, how do you actually go about trying to build a policy routing framework that's extensible? And again, you don't know what the routing protocols are going to look like that you're going to be able to want to configure. So the first question is, well, what is routing policy? Because I know not everybody really has a good idea of routing policy. Well, here's a pretty picture. That's basically all I want to convey here is that the network is really complex. And if you think that the network actually has nice, regular topologies and things like that, you look at these kind of maps and you go, not really. This is a router level map of the internet from about 6 years ago. Here from Kaida is a autonomous system level map of the internet, which basically shows longitude around the outside and degree of connectivity going into the middle. And you look at this map and you go, no, I can't really tell much from that either. So when it comes to routing policy and so forth, we tend to think of things like this, which, as you can appreciate, bears very little relationship to the real world. But this is the way we think about things in terms of different tiers of ISPs. The real world maps into this to a reasonable degree, but not completely. So first of all, I need to explain very briefly how BGP works for those of you who don't necessarily understand about BGP, and then I'll explain what policy is, and then I'll explain about how we actually go about trying to do that. So basically, what we want to do is to, from over here, to reach a network that's the other side of the world. And the routes basically propagate across the internet, and BGP, as it propagates them from autonomous system to autonomous system, accumulates an AS path, which basically records the path that the route actually took. The first main purpose of the AS path is to be able to detect loops. So something basically comes back to an AS that's already in the path, you actually detect that. But this is sort of the unimportant parts of BGP. The other thing the AS path is used for is to try and figure out, well, OK, these routes generally flood out across the internet, but we have to figure out which one to use. So in this case, this AS has received a route one way, and it also receives it another way. And the AS path is the first mechanism by which you choose one route over the other. Generally, in the absence of any other policy, you choose the shortest AS path. This is sort of the core mechanism of BGP. Now, the question is, what about policy? So here's a route. It flooded across the network, and it comes in over here. Well, this may be somebody's dial-up link or DSL line or something like that. So this is probably a bad idea to accept that route. So the normal thing is that you would only accept a route here if it came entirely from your customer, not if it came from other places. So this is the example of a policy that you might configure on a router here to not accept certain types of routes. I mean, other sort of policies you might want to do, this is an export policy, don't export routes to a provider. This guy doesn't want to export this route because if he does, this is some small ISP, this is AT&T and this is Sprint, we don't really want to carry all the Sprint AT&T traffic. Not really in our financial interest. Here's another one. We get the route two different ways. Which one would we prefer? Generally, you prefer customer routes because they're paying you money. If they're paying you money, you might as well use their routes. It's in your financial interest. All of these are the sort of things you need to configure on BGP to try and make this stuff actually work. So here are some more specific examples of the sort of things you do. Generally speaking, policy breaks down into import filters and export filters. So examples of sort of incoming filters would be to drop the BGP routes if the AS path contains a certain AS, things like that. Or also not just to drop routes, to change things. So you might set the local preference field on BGP or any of the other fields you might want to set. Export filters, again, you might want to say don't export routes to a particular peer if they have a particular community. Community is just a way of tagging routes with some arbitrary label. So you generally tag them in an import filter at one side of your network and evaluate the fields to the other side. And then things like this, which is actually fairly complicated. We want to redistribute OSPF routes that come from a particular OSPF area to BGP, and on those routes to set the BGP's multi-agency discriminator. I mean, this isn't actually a particular one you might want to use, but you can see the complication here. We're trying to build a policy framework that's going to be able to encompass just about any routing protocol. This one policy statement basically has to know about OSPF. It has to know about things that are totally OSPF specific. It has to redistribute routes from one routing protocol to another and set stuff on those routes which is totally BGP specific. And yet, we don't want our policy framework to have to know about either OSPF or BGP. So the question is, how do you actually go about trying to do this sort of thing? And it requires a certain amount of thought to figure out, well, what really is required. So if you look at the sort of staged architecture that we have, actually, it doesn't really matter quite so much whether you take our architecture or anybody else's architecture. There are basically a path that routes take through a router. They come in from the outside world, and so there's, in any routing protocol, there's kind of a decision process goes on as to which routes to actually use. It doesn't quite look like this in link state routing protocols, but for vector-based protocols it does. And so there's a point before decision where you might want to be able to interact with the routes. There's a point when you've actually chosen which one to use where you might want to interact with it. Then, of course, routes come from different routing protocols, and you have to choose which one of those is going to be used. So there's a point before and after that choice where you might want to be able to interact with a route and change it. And on the way out, similarly, you might want to interact it before you've figured out which route's winning. You want to choose some subset of routes that you want to redistribute on to other routing protocols. And then you might want to interact with the routes again before you actually send them out to the neighbor. So there are all these different possible places where you might want to be able to change routes. And if you try and design a unified policy framework that has to deal with all these different possible cases, the complexity gets pretty hairy. So after spending a lot of time thinking about this, we've ended up with a framework which it turns out you don't actually need to interact with routes in all those different places to implement just about everything we can think of that anybody ever does with routing policy. So the first stage you want to implement is, there's going to be 4 filter banks on here, but the first stage is basically the point of ingress. You want to be able to reject routes. You want to be able to modify them before you've made a decision as to which one to take, because you want to be able to set things like the preference values or that sort of thing. So that's basically for import filters. And for an import filter, you want to be able to match on a route there, and you also want to be able to modify the route. So the example I had earlier, set the local preference of BGP local preference field of 3 on those incoming routes if they have a certain BGP next hop. It's something that you would implement entirely at this point. It's an import filter. It gets entirely a pre-decision on the routing protocols. Export filters get complicated because they have to deal with things with many different pieces of state. This example I gave you just now, which basically has OSPF-specific information in there, that's basically some information about where the route originated, some information about where it's going to BGP, and it also, those routes have to be redistributed on. So it turns out that the export policies that you actually need to interact with the route in 3 different places. The first place you need to interact with it is after the routing protocols have decided which routes of one, you basically need to be able to match a certain subset of those routes. The second place you need to be able to interact with it is in the RIB. You need to figure out a subset of those routes to be able to redistribute onwards. And you'll also notice that actually, conceptually, this is one routing protocol here and here. So some routes basically go straight through from one to the other without going through the RIB and bypass that. And the third place you need to be able to interact with this is you want to be able to change routes before they actually go out to your neighbors, or in some cases, just not forward them on. So that's basically the 3 different places where you need to be able to interact with routes from the point of view of export filters. Dave? I'll show you in a second. Okay. So in the configuration part of the router, you basically need to be able to take policies like this. Obviously, they're not written in English, but you need to be able to take policies like this and see the big picture. See how this basically breaks down into different pieces of functionality that need to go where. So there's basically a policy engine that's going to look at these and figure out which bit of filtering needs to happen where. So the first thing that we'll do is to configure the stage 2 filter here. And in this case, we're configuring that on OSPF. And we're basically saying, match OSPF routes that come from this area. I'm going to tag those with an arbitrary tag. And this tag space is a globally unique tag space that's allocated by the policy engine. So this is why you need to be able to do it there. Is OSPF is the only thing that knows about OSPF area. Once it's in the RIB, you have no information about OSPF area. The RIB doesn't know about routing protocols, so it can't know about that. So this is the point at which you want to be able to interact with it. You want to be...
That's a design decision as to whether you can embed things into the RIB or what framework you can put in there. You're saying you don't put any information in the RIB. It doesn't necessarily even know which protocol it came from?
No, it knows which protocol it came from. But it doesn't know anything that is specific to that particular protocol because that would... I mean, okay, you could probably design a way that you carry opaque information through the RIB. But once you're carrying opaque information, you might as well deal with it in the place where it actually knows how to deal with that information. So in this case, all you need to basically do is to add these tags to the routes as they come through, and then you can match arbitrary protocol-specific information. The second place you need to be able to do this is to configure the filters in the RIB to say, we're going to redistribute only some routes. So we're going to redistribute routes that happen to have this tag in this case. It's a fairly simple policy, even though it happens to be a distributed one. And the third place is you want to be able to set the MED, and that's basically, it's a BGP-specific thing, so you ask BGP to do that. And that's basically how this policy breaks down into these 3 different places. Now, the question is, how do you actually implement these policies down inside each of these things? And again, you want to be able to do this in such a way that this is agnostic as to what it's actually configuring. So now we get into how the policy engine works. The first thing the policy engine does is basically to take a complete routing policy for the whole router. And it can figure out import filters go there, export filters need to be broken up into this from part, this to part, and what we actually do to the routes. It doesn't really know, it knows which routing protocols exist. And then it loads basically a type map, which basically, it's a lot bigger than this, but it basically says for a particular protocol, there are attributes of certain types. And some of those you can modify, and some of those you can only look at. But it doesn't know anything more than this. It just knows that there are these attributes by name, what their types are, to make sure that it only does operators on things which are correctly typed, and whether they read right. And basically what it then does is to write a simple stack machine program for each of those filters. There's a very simple programming language that it writes, and it downloads that program into those filter banks. So here we go, the policy manager in one of these filter banks in one of the protocols, and it looks the same no matter which of the protocols we're actually in. it has this generic stack machine filter, which is actually going to do all the work. A route's going to come in, we're going to run a little program over it, and it's going to do some work, and then the route's going to go on. So the route comes into your filter here. The stack machine gets invoked, and the stack machine basically says, I want to read these particular attributes from the route. And so it obtains these attributes by basically asking for them by name. It then may modify those attributes. It may modify some other attributes. It may say, drop this route altogether, things like that. And then once it's done that, the route can continue on. Now, the real key thing here is that basically all the filters, stage 1 through 4 filters, basically use the same stack machine, the same little programming language. So the policy manager basically just has to figure out which bit of policy needs to go where and make sure that it just configures those. This is basically just going to ask for these attributes by name. It's going to write them back by name. It doesn't have to know anything. All the sanity checking of which names actually make sense has been done in the policy engine for it by the fact that there's basically a static table of information. And so if you're implementing a routing protocol, all you have to do is to implement a filter stage in your protocol and implement the reader and the writer. And they, of course, are protocol specific. It's a very small piece of code to basically take a BGP route and, let's say, pull out the AS path or pull out the MED and give it to the stack machine. So this means that you can, with very little code, write a policy filter for any routing protocol you're writing. All the complicated stuff of difficult matching rules and things like that is handled basically by the stack machine in a generic manner, and it's not tailored towards the routing protocol itself at all. So that's basically the last of the three main sort of design sections I wanted to talk through for you. Basically, I've showed you the stage design we've used for BGP and for RIB, which hopefully greatly encourage extensibility. We've certainly found it useful when we've want to add functionality later on and hadn't thought of it at the start. Talked through very briefly the XRL inter-process communication mechanism, which lets us actually use scripting languages for testing and that sort of thing. It also allows us to use these template files for extending our configuration language. Talk through how that command line interface gets extended based on these template files. And briefly, I've talked through the policy routing framework. So the question you have to ask when you try, sorry, before I go on, Karen.
There's been some recent work at CMU or AT&T and other places where they try to separate the control plane from the forwarding.
Mm-hmm. You're talking about forces.
What do you comment on the extensibility of that kind of architecture?
It's a different part of the problem space. This is control plane functionality, whereas that is the interface between the forwarding engine and the control plane. So all of our work basically sits up there in the control plane part and communicates down with the forwarding engine. I won't flick all the way back to the relevant slide because it'll take me a long time to get back here. But if you think back to the block diagram I showed you at the start, there was a box on there labeled FEA. And from our point of view, all you need to do to make our work function with forces is to write the bottom end of the FEA for forces. And then it will work on a forces platform. And that's basically all you need to do to tailor it to work on a particular system. Because of this architecture, which tries to isolate the routing protocol so they don't need to do anything smart about talking to the net or anything like that. Any privileges, you can really isolate them and they can do very little damage. The FEA is then the one place where you have to tailor for a particular platform. This also turned out to be massively useful when we wanted to port this across to Windows and found that things weren't quite as we were used to.
Maybe you can take this offline, but this is not entirely, for forces they might be correct, but for the different software architecture, they've done things where I don't know whether the interface is that simple because they do things like run multiple OSPF processes together and they all have one control module and things like that. I don't know how that would work.
I can't really discuss it without having much more specifics to look at whether it's something we have thought of or not. Inevitably, when you try and design things for extensibility, you attempt to do a good job, but you don't always succeed in thinking of everything anybody might want to do. And so it's hard to discuss in the hypothetical without really going and seeing what they're trying to do. There's certainly no problem on our architecture with running multiple routing daemons and so forth. There's no problem in principle with running multiple RIBs. if your forwarding plane has some way of dealing with multiple ribs, but we've never done that, and it's down the line some way if we would actually do that kind of functionality. So just some simple performance numbers before we finish. One of the things we wanted to look at was how long it actually takes from a BGP route coming in to actually that getting into the kernel. So this graph basically was a fairly simple test. We fired in 200 and something routes, one a second, and got a new instrument of the code to find out where in the code the route passed at certain times. So the red dots on here are how long it took the route to actually, no, wrong. Rewind. I'll get onto that one in a second. So the x-axis here is the route number. The y-axis is how long it took in milliseconds for the route to come, first being seen by BGP to actually being into the kernel. And the different colors on here basically show the load that the router had at the particular moment in time in terms of routing table size. So the red ones here basically show when the router is unloaded, its routing tables are effectively empty, although there is a next hop already resolved, so we don't have to go and ask about that one. And it's around 3.1 milliseconds from when we first see the route to we actually end up in the kernel. And then the colored ones are basically, well, just to see whether we actually got the computational complexity right in these different parts of the protocols. How much longer does it take if we have a full BGP feed of 160,000 routes? So the green is basically where these routes are coming in on a peer which actually has held those 160,000 routes. And the blue ones are when it comes in on a different peer, but another peer has had 160,000 routes. And you can see there's a very small change of a lot less than a millisecond as you go from an unloaded router to a loaded router. So this, I think, generally shows that we're pretty fast in terms of when a route appears, how long it takes us to actually go through these different stage things, through BGP, through the RIB, through the FEA, and down into the kernel. It's an interesting question where the time goes. And this graph attempts to break that down, although inevitably by instrumenting it, you probably affect the thing you're trying to instrument. This is basically showing that the route basically came in, and then the red on here is when BGP queues it to go to the RIB. The green on here is when BGP thinks it's sent it to the RIB. The blue is when it actually is timed as arriving at the RIB, and so forth as it goes through. And what you actually see on here is that it spends very little time in each of the actual protocols. So the majority of the time is really that the protocol is doing something, and then we get a context switch and something else happens, and so forth.
And how do these lines slope and extend all the way out to 150,000? You're loading in a full peer.
This is with a full peer.
So, as in you're not giving it like 200 routes, but you're giving it all 160,000 routes of pure SMR.
Oh, okay. That's a different question. So what these graphs basically try to show is for a single route, when we have a large table, how long does that take? What you're asking is, when a router comes up, how long does it take to give you 160,000 routes? I don't think I have the numbers off the top of my head. Do you know? So 10 minutes on a very slow machine. We haven't put much effort into doing any optimization of any of this stuff at the moment. The 10 minutes, I believe, was still when we weren't even pipelining. Because obviously you get a big win here when that happens, when you pipeline a lot of routes between the different protocols. And for a while we were having some stability problems with the intra-process communication, so we turned off the pipelining. And I think that 10 minutes still has that, but stability problems have now been resolved. And I don't think we've actually done any tailoring to get the pipelining working as well as we ought to do. Again, the pipelining will work much better once we've actually sorted out our scheduling details to make sure that we actually do get stuff into the pipeline before you do a context switch. So I think we have a lot of confidence that we can get those numbers down by quite a bit, but I don't know where they're going to end up.
And that instrumentation is currently there, so anybody can enable it and try to spread themselves.
This one is going back to this question of being event-driven versus scanner-driven. Again, we have routes arriving once a second, and the question here is from when a route first arrives at BGP to when is it actually passed on to a BGP neighbor. And what we have here is XORP, MRTD, a fairly old Cisco router now. Do you remember what iOS it's running? 12 point something anyway. And Quagga. And if you look on here, what you see is this wonderful patterning. which is the root scanner running. So some routes arrive and the root scanner runs immediately. Some routes arrive and the root scanner doesn't run for 30 seconds. So you obviously get this nice linear decrease. And you can see that the MRTD and XORP are basically persistently down here around the few milliseconds timescale. And Quagga and the Cisco router you got an average delay of 15 seconds before before you bother to tell your neighbor that you've actually just heard something that you want to use. So that's just the properties that you see of the root scanner. It's really obvious in this kind of graph. I believe newer Cisco operating systems and routing code are moving towards being event-driven as well. So I can't say that all Ciscos are this bad, but.
I'm wondering how this event-driven style is the best latency or less affect the current dynamics of all.
There's been some research on that, although it's one of those experiments that's very hard to do without having this sort of stuff deployed because you don't have any instrumentation points in the network. But the general conclusion is that the delay of root scanners is very bad from the point of view of convergence and the dynamics of the internet. Because these delays tend to accumulate across the network, but they let something happen at one pace, something happen at another pace. But I'm hand-waving here because there isn't really a lot of understanding as to exactly how these things really impact the world. The other thing is mechanisms like root flap damping, which also seem to have a fairly serious adverse effect on the way the dynamics of the internet actually function. It's probably the wrong mechanism to use, is to try and actually slow the propagation of routing information. The better mechanism is to not generate an awful lot of churn in the first place, and that means you want to be suppressing it close to the origin, whereas trying to slow things down way through the network is the wrong place to generally deal with that kind of problem. But that's... it's easy to add delay. It's hard to remove delay from a system. So I think you basically want to design the system so that they function low delay as far as possible. But you can add delays later if they're shown to be a good thing. So in terms of current status, there's a fair amount of functionality here that we now consider to be pretty stable. BGP for V4 and V6, RIP for V4, V6, in sparse mode again, V4 and V6, IGMP V2, MLD for the V6, the RIB and the management framework are all pretty stable now. OSPF, the policy framework, and ISIS are in progress. ISIS is not on our immediate high priority list, but OSPF and the policy framework will be, we hope, stable by the end of the summer. The platforms that were supported on basically most of the BSDs and Linux, and the Windows port is in progress. Ottone will probably tell you more about exactly what in progress means here, but basically, to a rough approximation, it means the unicast routing protocols are working, the multicast ones aren't, and the command line interface is not working, but everything else is. V6 is not working, but we'll get to that one. So to summarize here, designing for extensibility is actually quite difficult. It requires you to really think about things from day one. It's not something you can ever retrofit. It's an architectural thing that has to permeate through the whole design. I don't have any good metrics, as you asked earlier, about how you evaluate extensibility. The only really good information we have is anecdotal evidence from people who have tried to apply XORP to stuff that we didn't expect. And they've come to the conclusion that it's fairly good for doing this sort of stuff. There's always this issue to do with modularity and extensibility versus performance. And this is inevitably a trade-off that you have to decide where you are in that space. For routing software, very high performance matters less than the fact that you actually scale well to very large routing tables. And it's not the same internet that it was a decade ago in terms of the balance between routing information and CPUs. We have a lot more CPU power now than we ever had in the past relative to the size of the routing tables. Now, this doesn't necessarily apply to backbone routers where you're trying to change hardware forwarding paths at very high rates. But in terms of the control plane, we actually have more CPU cycles available, and that really changes the landscape and the balance of power here. Really, only time is going to tell if XORP is ever adopted widely enough to change the way protocols are developed, tested, deployed, and so forth. we've been doing this for 5 years now, and it's really the last 6 to 9 months where the traffic on the mailing list has really started to take off and lots of people started to deploy XORP in interesting ways. I think at this stage, pretty much all of them are academic or research, but that's what we need. We basically need people to try it out, find where things really work and don't work, and the bugs to get fixed, and that way the software will get stable enough to see deployment in the wider internet. So thanks to all the people who have worked on XORP over the last few years, and there's going to be a lot more years ahead, I hope. Those of us with blue here are here today, Otanu, Pavlin, Bruce, and thanks to everybody who has funded XORP too, including Microsoft. Questions? More questions? Rich?
So in the beginning you were talking about how difficult it was to, you really spec Xarxes and those seem kind of straightforward when you implement it. It's actually quite difficult to get a good, robust model implementation.
Yeah.
So, I mean, is that a problem? Is that a deficiency in spec?
Yes.
I mean, in other words, if there were a better RFC out there, would that not be a problem if anybody could do it? Or is it some of the
I've spent quite a lot of time in the standards process of the IETF, as have you. The question in terms of writing specs is how much do you specify implementation versus how much you specify just the minimum need for interoperability. And I think that from the point of view of the standards documents, it's probably right to specify the minimum needed for interoperability. But that doesn't mean that there can't be additional documents that can help people out do good quality implementations. The problem in the past always was basically the only way to interoperate with Cisco was to, or well, to interoperate with anyone, basically was to interoperate with Cisco and test against their implementations. And it really wasn't in Cisco's interest to write good specs. I wouldn't go quite so far as to say they deliberately wrote bad specs, but they had no real incentive not to. The existence of Juniper rather changed that. And if you look at the BGP specs, for instance, they've got a lot better over the last few years. The rewrite of the new BGP spec is much, much closer to documenting a useful subset of the functionality and what's actually deployed. It's still pretty minimal in a whole bunch of useful places where you'd like more information. The OSPF spec actually is not too bad from an implementation point of view. It looks like they actually tried fairly hard to help implementers out.
And there are lots of examples.
But I think that certainly the specs are deficient. And we could do better. But you do want to separate out what is required from how you might implement it, because otherwise you seriously prejudice how you actually go about building something if you specify how you implement it rather than what it needs to interoperate. It's a tricky game, the standards game, to avoid getting caught up in all the antitrust mess and so forth. But I think some informational RFCs, for example, would really help people. And they wouldn't be mandatory, they would just be helpful.
Back on the early slide, you described what the problem was, and you think it was big there. And option 2, I think there's 2 different problems that you mentioned in option 2. One was it had to be extensible, and it had to be, ISPs had to be
Willing to deploy it, yeah.
So I think you made a decent argument that this is more extensible there. But the question is really the second aspect. Is this something that would be easier to get inside ISP to deploy than the existing things? And part of the question there is,
there's
be more stable in things like the multi-process model. But then the question is, out of the fear and the instability today due to things that crash, or is it just due to weirdnesses in the protocol implementation that process isolation wouldn't help you?
That's a good example.
well, multicast is also a good example, but
for an ISP, you'd have to show that you've sufficiently mitigated those things. That the majority of problems are actually due to protocol bugs
I agree.
and not crashing bugs. Then there's actually not any difference between the synthetic platforms in that respect.
But there's an example, isn't there? For example, at Berkeley, the campus has put in a totally parallel network to IPv6, even though they can run the same wiring and switch on IPv6 on their main router, they will not do it for the same reason. So
the other classical one was deployment of multicast,
right.
where
There's separate routers. The backbone is not capable.
Anyway,
But my point is that there are spaces like multicast and V6 where people want to experiment with them, where it's a much more compelling story maybe to say drop in a XORP router and do V6. For example, we had intended by this stage at our own border to be running XORP routers. So we're running a XORP router for V6. As soon as we got the policy story polished, we will run our own stuff at the border. So over time, you get more.
I understand that doesn't directly address my
No, but
my question is,
but it's a good question though, because
is this significantly more likely for ISPs to accept than the alternatives that are out there? I can agree that it's significantly more extensible, but is it significantly just the other half of the problem is the acceptance of ISPs?
So
that is significantly more likely to.
I can argue that it's better than the past, but I can't argue that it's sufficient. I mean, the classic example that you and I spent a lot of time doing was multicast. And loads of ISPs refused to turn up multicast because if any minor thing went wrong with pim implementation, then their BGP would go down. In an architecture like this, there is pretty much no way that the pim sparse mode is going to take BGP down. Generally, things are sufficiently well isolated. In terms of whether PIM multicast might then overload your network with traffic, that's a different question. And it doesn't give you that form of protection. But most of these ISPs along the same wires ran multicast and unicast traffic. So they obviously weren't too concerned about that one. They were more concerned about BGP going down.
But do you actually have some data about how often instability is due to a crash in the protocol?
Anecdotal evidence, but nothing more.
That would certainly help the case.
I mean, if you go and talk to folks in Nanog, a lot of the time they're really fairly scathing about the stability of anything other than in a fairly well-tested a small subset of the available functionality.
But is that because of crashes, or is it because it ends up overloading the network or some other reason?
No, it's primarily because of crashes.
So the original Cisco modcast problem was they were leaking memory crash.
Yeah.
So we would be, that bug we would be robust to. The other thing that we can do if your routing protocol is that experimental, you can actually run it on a different box. So if it's going to take all the CPU.
I agree with that. That same argument would apply to any of the other alternatives as well.
No, because we can actually take one router and move a routing protocol to a different box. We can run a distributed router and isolate that routing protocol. We're also playing around with running XORP under Zen. So we can actually use the virtualization environment to really isolate and bound a routing protocol. I can't say we're at the point where we're running that yet, but I have a student who's working on it. And that will give us an even stronger story in terms of how much we can protect the rest of the router from something going bad on that router. But it, again, doesn't protect the network, which is something which it might in principle be possible to do, but in practice, there's too much of a coupling there with the forwarding plane and exactly what you do in terms of rate limiting on the forwarding and so forth, for us to be able to solve that problem in the control plane. I think that it may be possible to, in a router where you control both the forwarding plane and the control plane, you may be able to mitigate that issue. But it doesn't seem to me that it's the main issue. But, of course, it may be for some people. Mark?
Given that some of this is going to be proven out in practice at the end of the day, can you just give us some sense of how many and what types of people have been downloading the software, educational institutions?
I don't think we've done enough analysis of the download logs to know for sure who has been downloading it. The traffic on the mailing list is an interesting mixture of people from various academic places, and we suspect, although we don't know for sure, that a number of the Chinese vendors are quite interested. They seem to have been asking fairly cryptic questions on the mailing list. So we don't really know exactly what their interest is, but it would be interesting to see how that plays out. In terms of number of downloads, do you actually recall off the top of your head? My recollection is that the last time we got Slashdotted, it was in the region of several thousand copies of the live CD were downloaded in about 6 hours. But I don't have the overall total numbers. There's a live CD of XORP which lets you stick a CD in it, and it will run a free BSD kernel with XORP running on top of it out of the box without having to compile or run anything. Sorry. So So let's deal with the Malay one first. It was something that we didn't consider from the outset. It just wasn't on our radar for some reason. It should have been. And then there was a guy in Canada, I forget what his institution was, who took XORP and decided to use it for doing some ad hoc routing. And the one problem he found was that we were assuming basically that you had to specify a next hop by subnet. And that doesn't work if you don't have subnet-based addressing. So that was one case where we had missed something. What we added was the ability to specify via the RIB a subnet via just interface. Sorry, a next hop via interface. And that problem went away, and he, as far as we can tell, was fairly successful in using it. In his particular case, I'm not sure that XORP actually helped him all that much, but we did actually manage to support him. As for the using this on other forwarding hardware, I think the answer is at this point we don't have a lot of experience with it. The FEA was designed to provide that isolation there, so we can tailor it towards different forwarding paths. But all of the forwarding paths that we have spent much time dealing with are software forwarding paths. So we obviously have experience with a number of different Unix kernels and using those as forwarding paths. We also have experience with Click, which is Eddie Cole and Robert Morris's very modular software forwarding path, where you can actually configure different elements and so forth. And more recently, we've been gaining some experience with using Windows as a forwarding path. But we don't actually have any direct experience at this point of using sort of switches or things like that. The stuff that Radia Perlman was suggesting. I honestly don't know enough about it to comment on it. I know its existence, but that's about all. Is there something specific about it that might be an issue, or does it just look like something else?
Forwarding might require
Yeah.
what they're doing is,
Was it layer 2 or layer 3?
yeah, exactly. So what they're doing is you have certain bridges which use channel 3. So instead of using channel 3, they want to use some link to protocol or something more stable.
But it was layer 2 forwarding, wasn't it? Yeah, so basically, XORP is not going to help you very much with that problem, because XORP is really intended to be an IP router, and so its concept of forwarding and stuff like that, at least in the existing implementation, is very well embedded with the concept of using IP for doing forwarding. So it's not going to help with that problem. It's not that it will... Sorry? Yeah, you can do it.
We're actually running a little late. Thank you very much, Mark.
Okay.
For doing that.
Thank you.
We are going to have a demo, and I think you can put it on both screens or switch back and forth. The routing running on Windows.
The microphone for you? Okay, it should be turned on. So, if it isn't, nobody told me.
So we came a few months ago to demonstrate XORP running. We produced our PowerBooks, connected to a FreeBSD machine back in ICSI, and then suddenly looked at the horror on people's faces when we discovered that we were expected to actually show XORP running on Windows. So hopefully this time we will fix that bug. Memorize that while we just set a couple of things up. So the demonstration that we want to do is we want to describe replacing your Junipers at the border with machines running Windows 2000 and XORP. So these are the two border routers. What did I say? Oh, okay, close. This is your ISP, and all of our experiments are going to be run from host 16. And I'm just going to switch inputs.
So that map is drawn on the whiteboard there.
Yeah, so you can refer back to it. Can you? And so lose the windows for a second. And so on this side, we're going to just run pings and trace routes from host 16. And on this side, we're going to control this router. Okay. So let me go back to the other diagram, memorize that, and we'll just start a couple of things running. So yes, so we've just started XORP running here and here. Let's look at the network. So our network configuration, as I described earlier, is our two border routers here, an ISP out there, and our test host. Let me just. So we should be able to, from host 16, ping our ISP's router. 1 second, Pavlin. Okay, Pavlin, could you ping the border router? Ha-ha! That's a nice thing about demos, isn't it? So, but it's okay. The reason that the ping is not going through is that we aren't running XORP on this router yet. So I'm going to switch inputs, or not. Okay, here we go. Pavlin, could you start XORP, please? And watch the oh, that's not good. Okay, try that again. So we're using the remote desktop to talk to XORP 1. Watch the ping at the okay, you've got okay. So when we
Keep poking.
Okay, here we go. So we're going to so we're starting XORP. So these are Windows binaries on XORP 1, slowly starting up. So the router manager is going through and starting the various modules that Mark told you about earlier. There we go, BGP, RIP, and then magically the ping will start running. And it did. Okay. Where's my... Oh, okay, I left it here. Where's my crib sheet? Okay, so let's... Pavlin, would you like to log into XORP 1? So this is our shell that controls the router. We don't have the shell running on Windows yet, but because of the XRLs, we can actually, on host 16, run the command line and control the router. So can you show me the configuration? So we have RIP enabled in the configuration, and if you go down to the BGP configuration, can you show me? We don't have the BGP pairings enabled at the moment. Okay, that's looking good. And could you show me the routing table, please? And we have command line completion in our... and there we are. And you can see that network is being announced in RIP. Okay. So, here we go. So next, I'm going to just switch back to the slides a second. And I'm going to go forward. So we've done the ping test. We've started XORP. So RIP is enabled, BGP is enabled, routing table contains that route. I was expecting to be able to display both at the same time. Okay, so what's going to happen? So we're bringing up a pairing with our ISP. We need to verify that if anything goes wrong, that the routing will continue to run. So we're going to actually disconnect XORP 1 from our ISP. Let me just switch back. So you can see that the ping is running from host 16 to our ISP. Now, please don't do this at home. I'm going to pull out this cable, and the ping is going to stop. And instantaneously, the routing is going to cut over. Okay, maybe it isn't. So we've actually configured it for 15 seconds. We actually wanted to show you that the ping stopped. And here we are. Back in place. So can you do a trace route for me? Okay, so we're going the long way around. Host 16, XORP 1, XORP 4, border. Keep running the trace routes. I'm going to put the cable back in. Okay, good. So routing's converged, the cable is back in, and you can't see the slides. Okay, so the route's configured 50 seconds, the ping is now running, you can see the new routing table. Let Pavlin show me the new routing table. Aha. Okay. And now, okay, that's what we just did. Okay, so now we want to see if we could. We need to see if we can. So now we have. We're going to enable BGP on XORP 1. And as soon as we enable BGP on XORP 1, we should be able to see external routes. So we're going to start a ping to an external route. Okay. So we have I guess we have Juniper-like syntax, and now Pavlin's going to go to the BGP config and enable the two BGP peerings. So that we have an iBGP peering to our neighboring router, and eBGP peering to the ISP router. And as with Juniper, when you make a change, we don't send the change. We don't. It's okay. It's okay. We don't send the change immediately, and you can see that the two parts of the config that we've changed are highlighted. So if you now commit the change, the pings should start running. Good. And if you show me the BGP routing table. So we're only at the moment we're just advertising that one network. Yeah. So and you can see the route is received both from on the iBGP peering and on the eBGP peering. So okay. Ta-da! Questions?
Can you just talk a little bit more about what you plan to do between now and October, and what enhancements you will do?
So we expect to have the IPv6 working. At the moment, we are not using the Router Manager v2 interface to install the routes, and we were hoping to talk to you guys today about how we can do that. We've had problems with the online documentation, and it looks like we need to see some example code for how to drive it. And so if we could have an interaction on that, that would be very useful. We will get the XORP shell running actually on Windows. So the problem that we hit was we didn't realize that our event loop is based on select. And we hadn't realized that select was not going to do the job for us if we have both IPv4 and IPv6. And it also isn't going to do the job for us for listening to the keyboard on Windows. So we're going to refactor that back in code and then that's one of the issues with the XORP shell. So refactor the backing code, and we should have a full story. We're not sure about multicast. We're still waiting for you guys to get back with us with the interfaces. But we expect by October to have a pretty full story. We haven't checked what we have into the tree yet. We can make, if somebody wants what we have at the moment, we can make that available.
That might be a good thing to happen for
And Bruce had an interesting question with. Actually, let me show you. Can you go to the top of the config? So if you see that our interfaces have interesting value, and we've actually used the interface ID at the moment, so that we have a mapping to this kind of the Unix byte space. And I'm told that identifier is different for V6 as well. Yeah. So does anyone have any ideas? Yeah. Yeah. So do you have any thoughts about how we can do the? Well, that's what Bruce was talking about doing. Yeah. No, we thought about having a separate attribute.
Yeah, you can do friendly name. Local space, area space, connection space, one, as an example. But that's user renameable.
Is that something that's fixed? Right. Okay. Okay.
That's kind of what we were afraid of, but we still need to pull all the NPR related bits to deal with that.
And we are. So you're saying something very different happens on Longhorn?
No, in addition to those, there's something still pretty good to expect.
Oh, okay.
None of those go away. Not an additional.
Right. So if we were to say that in the future we only worked on Longhorn, then we could deal with the thing that we were the naming that we were.
My suggestion would be fix a string there. Allow that string to be in any of those formats.
Right. Okay. And just if the user decides to rename something, that's the user's problem.
The same approach that we took in like the NetShell or the normal command line configuration thing. You can name your interface by GUID, by friend name, by index, whatever. It's easy to distinguish which one of those syntax it is.
Yeah, but the information that's passed to grid protocols, things like that, really want something that can be essentially handled by anything you packet. It's like when you configure the RIP, it needs to know the interface ID.
Right, just like you have a pipe, right? You have a 232, and so you can have a pipe you translate into a canonical binary form. No matter what it is, you can just like in 232, you can convert from ASCII into a binary format. I'm saying convert from multiple formats into a binary format. That's just because how.
I'm trying to figure out how many places you can know. If you can keep it down to a small piece of the core library code, then
I would expect, even if you kept the pipe code, you should have 232 in for it.
No, I didn't mean to do that.
I want to say thank you very much. Some of us are going to continue on to lunch so we can continue the specific discussion about some of the implementation. I say thank you all for coming up, Lord, and thank you all for coming.
So should we?